All right, so now we're ready to look at molecules as a whole. And the thing about molecules is they often have more than one bond. So if you've got something like HF, right, or you've got something like, let me see, CO, right, you essentially just have two atoms. So you really can't say anything other than the bond is polar or the bond is non-polar. But when you've got a molecule, you've got multiple bonds. So let me show you one. So carbon dioxide has a structure that looks something like this. This is its valid Lewis structure. And we can see that the shape of this molecule, what's it going to be? Well, you've got one thing repelling here, you got nothing repelling here, so two repulsions will give you that 180 degrees, that linear geometry. So the way I've drawn it is actually the shape of the molecule. Now, I ask you, what's more electronegative out of carbon and oxygen? Yep, oxygen is. So oxygen is 3.5 on the electronegativity scale. Carbon is 2.5. So what I can do is I can draw in the bond dipole. So in red here, these are my bond dipoles. Now, here's the thing about these dipoles. There's two of them. So although we can say each bond is polar, when we look at the molecule, we have to actually add up all the dipoles to see if the molecule itself is polar. And how are we going to do that? Well, one way to do that is to imagine each dipole is pulling, it's a vector if you like, in the direction that it's pointed. So this one is pulling directly to the right, and this one's pulling directly to the left. And so if you had an object in between, like a green lightsaber, if you are pulling to the left and you're pulling to the right, it's a tug of war, and the end result is it doesn't move at all, assuming it's pulling equally as strongly. And so what that means is that CO2 is actually a non-polar molecule. So the overall dipole is actually 0. So the overall, I could say the molecular dipole equals 0. So the bond dipoles cancel out. So we have to basically sum together the bond dipoles, this one pulling, oops, here's my lightsaber again, this one pulling to the left and this one pulling to the right to get my overall one. And there's actually a couple of different ways you can do this. So if you want to, you can actually take each dipole and you can kind of write them. You start at 1 and you write the 1, it takes you to the right, and then you write the second one right where the first one ends up, and it takes you right back to where you started. So essentially you can add these together by basically marching one to the right and then marching the other one to the left, and you can see you start and you end up in exactly the same place. So they cancel out, so that is exactly 0. What does that mean if the bond dipole is 0, or the overall molecular dipole is 0? Well, what that means is that you are a non-polar molecule. So the molecule as a whole is non-polar. Okay, so whenever you have an overall molecular dipole that is 0 and everything cancels out, then we say that the molecule as a whole is non-polar. Even though each bond is quite polar, overall they cancel out, just like being pulled. So if someone pulls your left arm and your right arm, right, or maybe two different people, one pulls from the left and one pulls from the right, equally hard, you don't move at all. You just stay exactly where you are, and maybe you got sore arms. Now, not everything's going to be like this. For instance, if you take a molecule like SO2, SO2 is a little more interesting because its Lewis structure, let's see, looks something like so. That is a valid Lewis structure. What is the geometry? Well, you got a bond, you got a lone pair. So 3 repulsions give you that trigonal planar geometry. So you got the sulfur and surrounded by those 120-degree angles. There's a lone pair, there's a bond to oxygen, there's a bond to oxygen. So you've got this shape here. Now, what about each bond? Is each bond polar? And the answer is yes, it is. What is more electronegative, sulfur or oxygen? Well, actually, oxygen is, and you can just look up the numbers, or you can remember that they're both in the same group of the periodic table. So if you look at your periodic table, there is sulfur, and there's oxygen, and there's selenium, and right next to it is fluorine, and so on. There's nitrogen, and you can see that sulfur and oxygen are in the same group. And remember, as you go up and to the right, it's more electronegative. So if you are sulfur and oxygen, it's really easy to tell which one's more electronegative because the one at the top is more electronegative. If you ever had them in the same period, the one further to the right would be the more electronegative. So if they're in the same group or same period, you can tell pretty easily. So what does that mean in terms of our dipoles? Well, our bond dipoles, so I've drawn those in red because red's a pretty cool color, right? Are pointing away from the sulfur towards the oxygen, so they look something like this. Now, what about the lone pair? Well, in this work here, we can just ignore the lone pair. We don't have to worry about it. So the question is, do they cancel out or do they not cancel out? And the overall dipole we can figure out by taking each bond dipole. So if we start with the one kind of pointing down to the left, and where it ends up, we start the new one, so it's kind of pointing down and to the right. Then you start at the top here, and you end up down here. So the overall molecular dipole, okay, I've drawn in green here, so this is the overall sum total molecular, I don't know how you say it, dipole. I guess technically it's a dipole moment, but we'll go. Looks something like this. And is it 0? No, it's not, right? So the steps don't retrace themselves. If they went back upon themselves, it would be 0. But you can see they kind of go straight down like that. In fact, if I draw that over the molecule, okay, it would look something like this. So this is the overall dipole moment here. I like to think about this. Imagine that you are pulling someone and they kind of scissor their arms forward and you're pulling one like this and one like this. The net result is the left-right motion would cancel out, but both of these are pulling down. So the overall movement of electrons in the molecules would be sort of from this side down to this side. So this would be your negative end of your molecule, and this would be your positive end of the molecule. And what do you think we call it when there's an overall dipole moment of non-zero? Yeah, that's it. And we call these molecules polar. So whenever you got a polar molecule, it means one end of the molecule is positive and one end is negative. You might say, who cares? Who cares if molecules are polar or molecules are non-polar? Well, there's a very nice rule of thumb called like dissolves like. And what that means is that polar molecules dissolve well in other polar molecules. And conversely, non-polar molecules, I'll use ditto marks here, dissolve very well in other non-polar molecules. So why do we care about this? Well, it turns out that water is a polar molecule. And so we'll look in a minute maybe why water is polar. And so that means that other polar molecules will tend to dissolve in water. So in your body, whenever you eat anything that is polar, it will preferentially dissolve in your water. Now, non-polar molecules, it turns out that things like fats and oils in your body are quite non-polar. They're primarily made of CC and CH bonds, and we've seen both of those bonds are non-polar. So that means that when you ingest non-polar molecules, they will preferentially dissolve in your fat. So if you take things like, say, vitamin C, which is polar, it will dissolve quite well in your watery tissues. It turns out also that you'll excrete polar molecules pretty easily. You'll just urinate them out. Whereas if you take non-polar medications, so things like vitamin D or other non-polar molecules, they tend to build up in your fat. They're not so readily excreted by your body. They don't dissolve in water so well. So they're not sort of carried around and carried out of your body very quickly. All right, so time for some examples. So I've told you water is polar, so maybe you can go ahead and you can figure out why water is a polar molecule. And then let me give you another molecule. Oh gosh, what's a good one? Let me pick something like CF4. Maybe you can tell me, is it polar or is it non-polar? And maybe something like Cl3, why not? So tell me if each one of these molecules is polar or non-polar. And on the exam, I would normally say, you can't just tell me that. You've got to write a Lewis structure. You got to write the shape of the molecule using VSEPR. You got to show me the bond dipoles. And then you got to make an argument as to whether they all cancel out or they don't. So pause the video and have a go, and then we'll meet back up again in a minute. All right, you ready? So let's start with water first. So water has a Lewis structure that looks something like so. So that would be the Lewis structure. We've got to convert it to a VSEPR structure. So we've got a bond, a lone pair, a bond, and a lone pair. So 4 repulsions gives you that tetrahedral geometry. Okay, so it looks something like so. 2 of them are lone pairs. I'm just going to pop them there. And 2 of them are bonds, so it's going to look something like that. So that's that bent geometry with that 104.5 degree angle between the hydrogens. Now, what's more electronegative? So you got 2 bonds here. What's more electronegative, oxygen or hydrogen? And the answer is oxygen. Oxygen is the second most electronegative atom on the whole periodic table, right after fluorine. So we know hydrogen's going to have its electrons pulled away. So the red ones here are the bond dipoles, and each bond is polar, but that doesn't actually tell us if the molecule is polar. And to figure that out, we've got to add them together. So you can kind of imagine here, if you've got one pulling down and you got one pulling sort of up and to the right, then the net result is, if you add them together, right, if you look at the pulling, is something that kind of moves in this overall direction here. So this is the overall molecular dipole. And if it is non-zero, right, that means that the molecule is polar. So we would consider water to be a polar molecule. And if we go to something like CF4, the Lewis structure for CF4 looks something like that. I should have picked maybe CH4. It would have been easier to draw because there's all these lone pairs around the outside. And yep, we have 4 repulsions. We've got a bond, a bond, a bond, and another bond. So that sounds like a James Bond movie here. So we've got carbon, and we've got that tetrahedron, right, where it is perfectly surrounded by 4 fluorines. And again, we've got what's more electronegative, carbon or fluorine? And the answer is fluorine. Fluorine actually kicks everyone else's butt, apart from another fluorine atom, right? Because fluorine against fluorine is a tie. And what we have here, we have 4 dipoles, these bond dipoles that point in equal and opposite directions. And so they actually all cancel out. The molecular dipole is actually 0 because all of these are pulling in opposite directions. So if you imagine, you've pulled yourself in 4 opposing directions, right? Everything would cancel out. So that makes this a non-polar molecule. So if you took something like CF4, it would actually dissolve in oil or fat, where something like water would dissolve in blood. If we look at something like NF3, we can write the Lewis structure for it, and it's going to look like so. So there's a lone pair, and the fluorines are all kind of identically arranged around the outside, like so. And if we count the number of repulsions, we got a bond, we got a lone pair, we got a bond, and we got a bond. So 4 repulsions gives us that same tetrahedral geometry. So there's my N in the middle, and there's my beautiful, gorgeous tetrahedral shape. So I'm just going to put my lone pair on the top because I think that's a good place for it. It looks tidier, and my atoms on the bottom. Do you remember the name of this geometry, by the way? Yeah, it's trigonal pyramidal. So the nitrogen's at the top of the pyramid, and the base is triangular, unlike the pyramids in Egypt. Now, we can ignore the lone pair here, so all we have to do is decide who's more electronegative out of N and F, and the answer is, of course, it's always F, so fluorine's going to pull electrons away from nitrogen, and in this case here, we've got 3, and they're all pulling down, so the bond dipoles, right, are all non-zero. The question is, what about the overall dipole? Well, they're all kind of pointing from the nitrogen at the top to each one of the 3 corners on the bottom of the triangle, so the overall dipole is going to point, if you like, directly from the top to a midpoint somewhere between those 3 fluorines. But the key thing is that it's not going to cancel out. It's going to be non-zero, the overall dipole. And what do we call a molecule with an overall dipole that's non-zero? Yep, the answer is it is a polar molecule. So NF3 would be a polar molecule.